Number 22 in section 3.4 is a really good problem to go over because it's pretty typical of a lot of the problems that we see here within this section. We've been given a position function. S of t is 600t minus 3t cubed. That's only valid for t values between 0 and 12, and we're talking about minutes here. So meters are our units for height, minutes are our units for time, and let's get rolling. Into part A, they want you to plot s and velocity v as functions of time. So what they're really asking you to do in part A would be to graph both of those. I'll come back to that a little bit later, I think. For those ones, honestly, guys, we're graphing a cubic function here for position. I would say you could probably just dump that into your calculator and be good with that. Let me move down to part B, though, real quick, where it says that we're supposed to find the velocity at t equals 8 and t equals 10. All right, guys, this is the big takeaway from 3.4. We now know that the velocity function of an object is given to us by taking the derivative s prime of its position function. So that function defined up above, 600t minus 3t cubed, we'll take the derivative using the power rule here and get a 600 and then minus a 9t squared, and that's going to be our velocity function. So they want us to find velocity at 8 and then also velocity at 10, and let's see here. I think both of those are going to be just a little bit messy, the first one. So let me just dump that into my calculator. 600 minus 9t squared is what we're doing here. So that'll be a 600 and then minus a 9, and our t value here was 8 for starters, and we were going to square that. So that's going to get us 24 then for our velocity at 8. Now they didn't ask for units, and I would generally tell you guys not to provide it if they didn't ask for it, but since we know here we were talking about meters for distance and minutes for time, that is going to be a rather odd velocity unit of meters per minute. That's what it is. And let's see, putting in a 10 now, I have a funny feeling how this might work. Let's see if I'm right. 600 and then minus 9. This time our time value is 10, and we're going to square that. Nope, I was wrong. All right, we ended up with negative 300 then for the velocity at this moment here. So negative 300, gotcha, meters per minute. Now, two things I want to point out right now. The fact that v of 8 is positive means that at this moment right here, the object still had to be moving up. Its position was increasing at that point because its velocity was positive, but now at v of 10, the object, the helicopter, is now moving back down now because our velocity is negative. Now that means, if I know what I think I know about the intermediate value theorem, that means that this object right here, if it was rising at 8 minutes and then falling at 10 minutes, its velocity had to equal 0 for some value of time in between 8 and 10. That's kind of what the intermediate value theorem would tell us right there. And I tell you what, let me maybe come back to that idea. Let me move on to part C right now. Find the maximum height of the helicopter. Okay, so for the maximum height to occur, yeah, that does tie in with what I was just discussing at the end right there. The maximum height has to occur when your velocity function, v of t, is going to change from, here we go, from positive to negative. Now to do that, we've got to figure out where v of t, your velocity function, which was a 600 minus a 9t squared, we've got to figure out where that's going to equal 0. So let's solve that. Not a real tough one to do by hand, although I think I'm going to need my calculator here in a minute. 600 is equal to 9t squared. We would divide out that 9, and I know that 600 over 9 would simplify. Both of those are divisible by 3. But I'm going to need my calculator anyway to take the square root of that because I don't think that's going to be a perfect square. So at that point then I might as well just leave it as 600 over 9 and let my calculator do all the hard work for me. So the square root of 600 divided by 9, and remember guys, your calculator, oh no, it went right to the decimal right there. Never mind. So we end up rounding to the nearest thousandth, everybody, with 8.165 is where we would write that out. 8.165. And as I expected to see, that time value here at which v of c is equal to 0 is in between 8, when the helicopter was still going up and 10 when the helicopter was coming back down. I expected that C value to be in between 8 and 10, and we found it there at t equals 8.165. Now notice I have not answered the question yet for part C. Find the maximum height of the helicopter. And what we found right here was a time value, 8.165 minutes. So we are not done with this one just yet. Let me mess with my zoom here a little bit, guys. What we now need to do is analyze the position function given way up at the top of this thing at this particular value of time. So we need the position function, 600t minus 3t cubed. All right, let me write that out here. So S of t was 600t minus 3t cubed, and we're now going to analyze that position function at t equals 8.165 minutes. Now, I don't think we need to write all this out. I'm going to go to my calculator and put that in, but a little reminder, guys, and I hope we've learned this lesson by now, we are never going to manually type in a rounded decimal for an irrational number. I'm going to use last answer on my calculator. So 600t minus 3t cubed is going to look like 600, and we'll do times, and where do I get to answer on here? I should remember that. If I hit that, there you go. So that's 600t, and then minus a 3, that's getting multiplied by, again, for you guys, it's control answer right there, and that answer is being taken to the third power. Let me double check that. 600t minus 3t cubed. Yeah, that's what it should be, and our answer here looks like the max height of our helicopter is going to be 3265.986. 65.986, and since we're measuring a distance or a height here, everything was going to be in meters here, and that is the answer then to part C. So again, guys, I didn't actually do part A, but I think all you would need to do at that point would be to plot that on your calculator, and I think you guys will do fine with that. That's not a function, either the position or the velocity, that I would need you guys to be able to graph by hand. So go ahead and use the calculator for the graphs on part A, and then here's what we have for parts B and C, and that's a wrap then on number 22.